Good morning everyone. Welcome to another video lecture of this course. Today we're going to learn about Euclidean and extended Euclidean algorithms, which are the useful tools in finding the greatest common divisor of two positive integers and writing the GCD of two positive integers in terms of the linear combination of those integers. In our previous lecture, we have learned about prime factorization and how to use the prime factorization in building a simple algorithm to compute the greatest common divisor of two positive integers a and b. And based on this algorithm, first we factorize a in terms of product of primes, where p1, p2 and up to p of m are primes. So a can be represented as the product of p1 to the power a of 1, p to the power a of 2, and all the way up to pm to the power a of m, where a1, a2 and up to a of m are non-negative integers. And b is factorized as the product of primes, where b is written as the product of p1 to the power b1 times p to the power b of 2 and all the way up to pm to the power b of m, where b1, b2 and up to b of m are non-negative integers. Then we can use this prime factorization representation of a and b in computing the greatest common divisor of a and b by using this formula. The GCD of a and b is going to be equal to the product of all those primes which appearing either in prime factorization of a or prime factorization of b. So for example, here we have m primes. So p1 is my first prime, p2 is my second prime, and all the way up to pm is going to be my last prime, which is appearing either in a prime factorization of a or in a prime factorization of b. So the GCD of a and b is the product of all those primes, and you choose the power of those primes which is the minimum number appearing either in the prime factorization of a or in the prime factorization of b. So for example, for the p1 prime, the power of p1 is the minimum of a1, b1. The power of p2 is the minimum of a2 and b2, and the power of pm is the minimum of am and bm. Let's take one example to see how this prime factorization based algorithm is applied to compute the GCD of two positive integers. So for example, my a is 12 and b is 16. Then the first step is to write the prime factorization of a and b. So the 12 can be written as 2 times of 3, which is equal to 2 to the power 2 times 3 to the power 1. While 16 can be written as 2 times of 2, which is going to be equal to 2 to the power 4. And in the prime factorization of a, we have 2 primes, 2 and 3. And in the prime factorization of b, we have only 1 prime, 2 is appearing. So we can rewrite them, and the prime factorization of a is going to remain same as 2 to the power 2 times 3 to the power 1. While the prime factorization of b can be written as 2 to the power 4 times 3 to the power 0. And if you apply your prime factorization based technique to compute the GCD, then the GCD of a comma b, which in this case is the GCD of 12, 16, is going to be equal to the product of primes which is appearing in the prime factorization of a and b. They are 2 and 3. So it's the product of 2 and 3. And then you choose the minimum power appearing in those prime factorization. So the power of 2 is going to be the minimum of 2, 4. And the power of 3 is going to be the minimum of 1, 0. Which if you simplify is the product of 2 to the power 2 times 3 to the power 0, and the GCD of these two integers is going to be equal to 4. So the prime factorization based algorithm to compute the GCD of two positive integers is a very simple way to compute the GCD, but computationally is not an efficient algorithm because prime factorization is a computationally expensive procedure and there is no polynomial time algorithm known for that. So we can say this computation of the GCD based on the prime factorization is going to be exponentially in time based on the complexity. In this lecture today we're going to learn about some efficient way to compute the greatest common divisor of two positive integers, which is based on Euclidean algorithm. To understand the idea behind the Euclidean algorithm, let's take one example and consider your a and b as 12 and 8. Then since 12 is bigger than 8, so based on your division rule, 12 can be written as 1 times of 8 plus 4, where 1 is my quotient and 4 is my remainder, 8 is the divisor and 12 is the dividend. If you rewrite and take 1 times of 8 to the left side, so you can also represent that as 12 minus 1 times of 8 is going to be equal to 4. From this expression on the left side, you can say any common divisor of 12 and 8 is going to divide the whole left hand side, which is 12 minus 1 times of 8. And since 12 minus 1 times of 8 is going to be equal to 4, so you can make a statement here that any common divisor of 12 and 8 also divides 4. And 4 is the remainder here. Now if you look at your original expression, which was 12 was written as 1 times of 8 plus of 4, you can make the similar observation here and can make a statement that any common divisor of 8 and 4 is going to divide the whole right hand side, 1 times of 8 plus 4, and since 1 times of 8 plus 4 is going to be equal to 12, so it's also going to divide this 12. So the statement which you can make here is any common divisor of 8 and 4 also divides 12, and 12 is the dividend here. So based on these two statements that any common divisor of 12 and 8 also divides 4 and any common divisor of 8 and 4 also divides 12, you can say that the GCD of 12 and 8 is going to be equal to the GCD of 8 and 4, because once they have the same common divisor, they will have the equal greatest common divisor. Now if we continue the same process with a new value of a and b, where a is going to be equal to 8 and b is going to be equal to 4, then since 8 is larger than 4, so we can write 8 in terms of 4 as 2 times of 4 plus of 0. So the quotient is 2 here and the remainder is 0. And because 4 divides 8, then it follows from there that the GCD of 8 and 4 is going to be equal to 4. And since we know that the GCD of 12 and 8 is going to be equal to the GCD of 8 and 4, and we already know the GCD of 8 and 4 is going to be equal to 4, so we can use this result in concluding that the GCD of 12 and 8 is also going to be equal to 4, and therefore we solved our original problem. The another observation which you could have made from this expression of 8 is going to be equal to 2 times of 4 plus of 0, that if you take this 2 times of 4 to the left side, you can write this that 8 minus 2 times of 4 is going to be equal to 0. And based on our earlier analysis, we can say any common divisor of 8 and 4 is going to divide 0. And if you look at your earlier expression, we can also make the similar observation here that any common divisor of 4 and 0 is going to divide your given integer 8. And similar to our earlier analysis, we can conclude here that the GCD of 8 and 4 is going to be equal to the GCD of 4 and 0. And the GCD of 4 and 0, where one of the integer is already 0, is going to be equal to 4. So let me recall what we did here. So we start from the original problem, which was to compute the GCD of 12, 8, and based on applying the division algorithm and finding the common divisor, so we proved that the GCD of 12 and 8 is the same thing as the GCD of 8, 4. And if you further apply your division algorithm and do the analysis of the common divisor, then you can say that the GCD of 8 and 4 is going to be equal to the GCD of 4, 0. And the GCD of 4, 0 is going to be equal to 4. So the GCD of 8, 4 is also going to be equal to 4, and the GCD of 12, 8 is also going to be equal to 4. So based on this fact, the GCD of my original problem 12, 8 is going to be equal to 4. And this is the idea behind your Euclidean algorithm. So you start with your original problem where you have to compute the GCD of two positive integers. Then you apply the division rule and you make an equivalent problem where now you have to compute the GCD of some smaller integer and then further some smaller integer till the time then one of the integers become equal to 0. And once one of the integer out of those two integers become equal to 0, then the GCD of that problem is going to be the non-zero integer, which is 4 here. And because of this equivalency, you can say that the GCD of your original problem is going to be equal to that particular non-zero integer which is left at the last step. Okay, so this is the idea behind your Euclidean algorithm. So we can write that in the form of a simple text. So how this Euclidean algorithm works? So we use the successive divisions to reduce the problem of finding the GCD of two positive integers to the same problem with smaller integers until one of the integers is 0. And the non-zero integer left at the last step is going to be the GCD of your original problem. So the main idea behind Euclidean algorithm is based on this mathematical result, which is written in the form of this lemma here. So according to the statement that A is equal to B times of Q plus R, where A, B, Q and R integers, then the GCD of A and B is going to be equal to GCD of B and R, where A and B are your dividend and divisor, and B and R is your divisor and remainder. To prove this lemma, where we have to prove that the GCD of A and B is going to be equal to the GCD of B and R, where A can be written as B times of Q plus of R. Our idea is to show that this pair of A and B and R, they will have the same common divisors. Because if they have the same common divisors, then you can imply from there that they will have the same greatest common divisor. To prove that A and B and R have the same common divisor, we need to prove that D is a common divisor of A and B if and only if D is a common divisor of B and R. So since this statement contains if and only if a conditional statement, so we can write the proof of this statement in two parts. So first we assume that D is a common divisor of A and B, and then we will try to prove that D is also a common divisor of B and R, and then we do the converse of that statement. So in the first part, suppose D is a common divisor of A and B. That means D divides A and D divides B. And from our previous theorem, which we proved in the divisibility lecture, that we know if D divides A and D divides B, then you can implies from there that D divides m times of A plus n times of B for some integers m and n. Now if you put a value of m equal to 1 here and n equal to minus of q here, then you can make a statement that D divides A and D divides B implies that D divides A minus B times of Q. From the statement of this lemma, we know that A is going to be equal to B times of Q plus of R. So we can write that A minus B times of Q is going to be equal to R. And since A minus B times of Q is going to be equal to R, so thus from this above statement, we can conclude that D divides R. Okay, so we are saying this also implies D divides R. Thus we proved here that if D divides A and D divides B, then this implies D divides R. Okay, so hence D is a common divisor of B comma R. So we start with the statement that if D is a common divisor of A and B, then this implies D is a common divisor of B comma R. Similarly, we can prove the converse of that statement, and this time suppose D is a common divisor of B comma R, that means D divides B and D divides R. Then again we can use our earlier result with respect to the value of m equal to q and n equal to 1, and from that statement we can conclude if D divides B and D divides R, then this implies D divides B times of q plus R, where you put the value of m equal to q and n equal to 1. And since A is going to be equal to B times of q plus R, then we can get from there that this implies D divides A. And hence we proved that D is a common divisor of A comma B. So by combining this implication statement and the converse of the implication statement, we proved here D is a common divisor of A and B if and only if D is a common divisor of B and R. So that means the pair A and B and R, they will have the same common divisor. And if they have the same common divisors, then you can say their greatest common divisor is going to be equal. And that's the reason you are claiming that the greatest common divisor of A and B is going to be equal to the greatest common divisor of B and R. So now we are in the position to describe our Euclidean algorithm. According to the lemma, we can use the recursive strategy to compute the GCD of two positive integers A and B. So to compute the GCD of A and B, you can build a base case. So if one of the integer, let's suppose if B is 0, then the GCD of A and B is going to be equal to A. Otherwise, you're going to call this recursively and compute the GCD of B comma A mod B. And in that case, you are updating the value of A and B, and A mod B is going to be equal to your remainder when you write A as B times of Q plus of R. So thus remainder R is basically your A mod B. Okay, and the claim here is that we will eventually hit the base case. In this recursive case, you are applying your successive division to making those integer smaller, and up to the point that one of the integers become equal to 0, and once the integer b becomes equal to 0, then the GCD of your problem is going to be the another integer a, which is your base case. So you can represent this Euclidean algorithm in the form of this figure. So where you're supposed to compute the GCD of the given integer a and b, and you're going to check if b is going to be equal to 0 or not. If b is going to be equal to 0, then the GCD of a and b is going to be equal to a. Otherwise, you're going to update the value of a and b based on this rule. So b will become your new a, and a mod b will become your new b, and then again you check whether b is going to be equal to 0 or not. If b is not equal to 0, then you're going to go to this loop recursively till the time b will become equal to 0. And once b becomes equal to 0, then the GCD of this problem is going to be equal to a. So here you have used this idea that the GCD of a and b is going to be equal to the GCD of b comma r, which is going to be equal to the GCD of b comma the remainder r is your a mod b. Let's look at one example to see how this Euclidean algorithm works. So here we're supposed to compute the GCD of 72 and 20. So in my initial step, I'm going to pick the value of a and b. So the value of a is going to be the larger integer, which is 72 here. The value of b is going to be the another integer, which is 20 here. Since the value of b is not equal to 0, I'm going to move to the next step. And in my next step, the new value of a is coming from the value of b from the previous step. So the a becomes 20 here, and the new value of b can be obtained based on the algorithm as a mod b, and from the value of a mod b, which was the remainder in the previous step, you have a b which is 72 mod 20, and 72 can be written as 3 times of 20 plus of 12. So the 12 is the remainder here, which is your 72 mod 20, and your new value of b is going to be equal to 12 here. And again you check the value of b, which from this step is not equal to 0. So you're going to shift that value of b to the new value of a. In the next step, the value of a becomes 12. The value of b is coming from the remainder from the previous step. So 20 can be written as 1 times of 12 plus of 8. So 8 the remainder here, which is your 20 mod 12. So the new value of b from here is going to be equal to 8. And then again you check the value of b is not equal to 0. So you move to the next step. The new value of a becomes 8 here. The value of b can be obtained from 12 mod 8. And 12 can be written as 1 times of 8 plus of 4. So the remainder is 4 here, which is your 12 mod 8. And new value of b is going to be equal to 4. And again you check the value of b, which is not equal to 0. So you move to the next step. And your new value of a becomes equal to 4. The value of b you can compute based on 8 mod 4. And 8 mod 4 you can write as it's going to be 8 can be written as 2 times of 4 plus of 0. So 8 mod 4 is going to be equal to 0. So the new value of b is going to be equal to 0. And once the value of b equal to 0, then you stop there. So based on your algorithm, the another integer a is going to be the GCD of your problem. So the GCD of 72 and 20 is going to be equal to 4. There is another way to represent the steps of your Euclidean algorithm in the form of a table, and I personally feel this is the best representation of a Euclidean algorithm. So to compute the GCD of two given positive integers, and which in this case is 25 and 60. So I can make my table with 4 columns, where first column is with respect to the quotient q, the next column is with respect to the integer a, and then the integer b, and the last column is with respect to the remainder r. So first I need to fill up the a and b value. So by looking my problem, and here I have to compute the GCD of two integers, and I will choose the larger integer at the place of a. So in this case, the 60 will be my a and 25 will be my b. Okay, remember the criteria here is you choose the larger value here and you choose the smaller value here. Okay, and for this choice of a and b, you can write 60 in terms of 2 times 25 plus of 10. Okay, so this becomes your quotient. So the 2 is the quotient here and 10 is the remainder here. So you fill up those values. 2 is the quotient here and 10 is the remainder here. Okay, so this is the first step of this algorithm. And then you do the shifting of column. So this 25 will shift for A and this remainder R will shift for your place B. Okay, so now you got the new value of A and B, which is 25 and 10, and 25 can be written as 2 times of 10 plus of 5. So 2 is the quotient here and 5 is the remainder here. So you can fill up those values as 2 and 5. And again you shift those B and R to the place of A and B. So your new value of A is 10 and the new value of B is 5. And for those value of 10 and 5, you can write 10 as 2 times of 5 plus of 0. So the quotient here is 2 and the remainder here is 0. So you put it here 2 and you put it here 0. And then again you do the shifting of those number. So here you will have the 5, here you will have the 0. And when you have the choice of A and B as 5 and 0, then you know you cannot find the quotient, you cannot find the remainder there. So for the case when your B becomes equal to 0, you stop. And the GCD of your problem, which was 25, 60, is going to be equal to 5. Okay, and 5 was the another integer here. Okay, so this is the GCD of your problem. So I found this table method is a very neat way to represent your steps of your Euclidean algorithm, and you can easily see the updated value of A and B in every steps, and by checking the value of B at every steps you can decide whether to stop the algorithm or not. So once the value of B becomes equal to 0, the another value of integer A, that's going to be the GCD of your problem. So after computing the GCD efficiently based on your Euclidean algorithm, the next thing we want to learn whether GCD can be expressed as the linear combination. So in particular, we are interested if we know the value of GCD of A and B, can that be expressed as a linear combination in terms of those positive integers A and B. And this GCD as a linear combination is your famous Without theorem. So according to the statement, if A and B are the positive integers, then there exist integers s and t such that the GCD of A and B can be written as s times of A plus t times of B, where this identity becomes your Without identity. And these coefficient s and t, they are the Without's coefficient. So we can use the Euclidean algorithm to compute these coefficients s and t, and this is basically your extended Euclidean algorithm when you are trying to represent the GCD of positive integers A and B in terms of the linear combination of those two positive integers. So let us look at one example, and through this example we are going to learn how to apply the extended Euclidean algorithm, where we want to express the GCD of 72 and 20 as the linear combination of those two integers. So this problem is, can you represent the GCD of 72 and 20 in terms of some linear combination of 72 and 20? That means can it be written as s times of 72 plus t times of 20 So can you find those two coefficient S and T, for which you can write the GCD of 72 and 20 is going to be equal to S times of 72 plus T times of 20. So the first step of the extended Euclidean algorithm is to find the GCD of those two positive integers. That means we're going to apply the Euclidean algorithm here. So I'm going to show those steps here in the first column, where the updated value of A and B is written in the second and third column. So in my initial steps, the value of A is 72, the value of B is 20. So 72 can be written as 3 times of 20 plus of 12. And since in this step, the value of B is not equal to 0, I can move to the next step. And in my next step, the value of A is going to be 20. And the value of B I can compute based on the remainder from the previous step, which was the 72 mod 20. So that's going to be your value of B. And from my previous step, the 72 mod 20 is going to be equal to 12. So I have the new value of B, which is 12 here. And again, the B is not equal to 0. So I can move to the next step. So my value of A becomes 12. And the value of B I can compute if I represent 20 in terms of 1 times of 12 plus of 8. So 8 is my remainder, which is the value of 20 mod 12. And in that case, my B becomes equal to 8. Okay. So once your B becomes equal to 8, again you check the value of B is not equal to 0. And if you follow this procedure, you can write 12 as 1 times of 8 plus of 4. And the next value of A is going to be equal to 8, and from this remainder, your next value of B becomes equal to 4. And again you check the value of B, and since you have A as 8 and B as 4, so 8 can be written as 2 times of 4 plus of 0. So remainder in this step is going to be equal to 0. So next time your A is 4 and your B is going to be equal to 0. And once your B becomes equal to 0, then you stop there. And the GCD of your problem is going to be your integer A. Okay. And your integer A in this case is going to be 4 in this last step. So the GCD of 72 and 20 is going to be equal to 4. Okay, which is the solution of this problem. So after this first step, where we apply the Euclidean algorithm to finding the GCD of 72 and 20, which came out to be equal to 4. So the next question we are trying to answer whether the GCD of 72 and 20 can be written in terms of the linear combination of 72 and 20. That means whether it can be written equal to S times of 72 plus T times of 20. Okay, so can you find those value of the coefficients S and T? Okay, and since the GCD of 72 and 20 is 4, so in another word we are asking this question that whether 4 can be written as S times of 72 plus T times of 20, then find those values of S and T. So in the second part of your extended Euclidean algorithm, you're going to follow this substitution steps. So in the substitution steps, you're going to visit your Euclidean algorithm and see if you can substitute some values from there or not. So from your first, second and third step of your Euclidean algorithm, you can say from the step 1, 72 is written as 3 times of 20 plus of 12. So from there, you can rewrite 12 in terms of 72 minus 3 times of 20. Okay. So from the step 1, we wrote 12 in terms of 72 and 20. Similarly, from the step 2 of your Euclidean algorithm, you use that 20 can be written as 1 times of 12 plus of 8. So from here, we can rewrite, if we write 8 in terms of 20 and 12, so we can say 8 is going to be equal to 20 minus 1 times of 12. Okay. And since 12 is already having the value from the equation 1, so you can substitute that value for this 12 here. So if you put this value here, so the value 8 can be written as 20 minus 1 times of 72 minus 3 times of 20, which if you simplify is going to be equal to 20 minus 1 times of 72 plus 3 times of 20, and that will be equal to 4 times of 20 minus 1 times of 72. So here you have represented 8 in terms of 20 and 72, which is going to be equal to 4 times of 20 minus 1 times of 72. And let's put this is your second equation. Now if you go to your third step of your Euclidean algorithm, so from your third steps you have written that 12 was equal to 1 times of 8 plus 4. So from here you can say 4 is going to be equal to 12 minus 1 times of 8, and then you can use your first and second equation to substitute the value for 12 and 8 in terms of 20 and 72. So using your first and second, you can say using first and second, we get that 4 can be written as 72 minus 3 times of 20, which is the substitution for 12, minus 1 times of 8, and the substitution for 8 is 4 times of 20 minus 1 times of 72. And if you simplify, this side will be your 72 minus 3 times of 20 minus 4 times of 20 and plus 1 times of 72, which will be equal to 2 times of 72 minus 7 times of 20, and you can rewrite as 2 times of 72 plus minus 7 times of 20. So you have represented 4 in terms of 2 times of 72 plus minus 7 times of 20, and from there if you compare, the 4 was your GCD of 72 and 20. So you have represented the GCD of 72 and 20 in terms of 2 times of 72 plus minus 7 times of 20. So on comparing with your original problem, where you are trying to find the value of S and T such that the GCD of 72 and 20 can be written as S times of 72 plus T times of 20. So from here you get the value of S equal to 2, and the value of T is going to be equal to minus of 7. Okay, so the extended Euclidean algorithm, where we supposed to represent the GCD in terms of the linear combination of two positive integers, we need to perform this procedure in 2 steps. The first, we compute the GCD of A and B, and in the second step then you do the substitution and find the value of those two coefficients S and T. In our next example, we will show the table method to represent the steps of your extended Euclidean algorithm, where we first obtain the GCD of 72 and 20, and then we will find as the linear combination in terms of 72 and 20. That means we are trying to find the value of those coefficients S and T. So based on my table approach, I will have 10 columns now. So the first 4 columns is going to be the similar column what you have in your Euclidean algorithm. So the Q is for quotient, A is for your given integer, B is your another given integer, R is your remainder, S1 and S2 are temporary variable, S is your coefficient, T1 and T2 is your temporary variable, and T is your coefficient, where the value of S and T can be obtained based on this formula, where S is equal to S1 minus Q times of S2, and T is going to be equal to T1 minus Q times of T2. So once we know the value of quotient Q and then know the value of S1 and S2, I can compute the value of S based on this formula, And similarly, if I know the value of T1 and T2, and if I know my quotient Q, I can take those values and use this formula to compute my T coefficient. So we are applying the extended Euclidean algorithm to obtain the GCD of 72 and 20. So in the first step, you fix the value of A, and A is the largest integer here, and out of this 72 and 20, 72 is the larger value, so the value of A is 72. The value of B is going to be equal to 20. In the first step, I choose the value of S1 1, and the value of S2 is going to be equal to 0. The value of T1 is 0, the value of T2 is 1, and all other values I can obtain based on my formula and based on my division rule. So since 72 can be written as 3 times of 20 plus of 12, so my quotient will become 3 here, and my remainder is going to be equal to 12 here. So I will put a quotient 3 and remainder 12 here, and then I can use this formula where S is going to be equal to S1 minus Q times of S2, and T was equal to T1 minus Q times of T2. So based on this rule, since S1 is 1, S2 is 0, and Q is going to be equal to 3, so the value of S here is 1. Okay. Similarly, I can compute the value of T. So T1 is 0, T2 is 1, and Q is 3, so the value of T is minus of 3. So this completes my first step of my extended Euclidean algorithm. In the second step, first you do the shifting. So the shifting, the B will become your new A. So the B is A is 20 now. Your remainder becomes new B. So the B is going to be equal to 12. The S2 will become S1, which is 0. The S will becomes your S2, which is going to be equal to 1. And the T2 will become your T1, which is going to be equal to 1. The T will become your T2, which is going to be equal to minus of 3. And all other values you can obtain based on your procedure, as since your value of A and B is 20 and 12. So again 20 can be written as 1 times of 12 plus of 8. So the quotient here is 1 and the remainder here is 8. So the value of Q is 1 and the value of R is going to be 8 here. And for those value of Q and R, you can obtain the value of S based on this formula of S1 minus Q times of S2. So S1 is 0 here, Q is 1 here, and S2 is 1 here. So the value of S is going to be minus of 1 here. Okay. And similarly, the value of T can be obtained from T1 minus Q times of T2. So T1 is 1 here, T2 is minus 3 here, and Q is 1 here. So this gives the value of T as equal to 4. Okay, and this completes the second step of extended Euclidean algorithm. Then again I will do the shifting. My A will be equal to 12 now, and B is going to be equal to 8. The value of S1 is 1, the value of S2 is minus 1, the value of T1 is going to be minus 3, the value of T2 is going to be equal to 4. And again I follow the similar procedure. So for the value of A equal to 12 and the value of B equal to 8, I can write 12 as 1 times of 8 plus of 4. So my quotient is 1 here, the remainder is 4 here. So the value of Q is 1 here and the value of R is 4 here. Okay. And again I can apply my formula that S is going to be equal to S1 minus Q times of S2, where S1 and S2 has the value of 1 and minus 1. So Q has a value equal to 1 here. So if I apply this formula, then the value of S is going to become equal to 2 here. and the value of t based on the formula of t1 minus q times of t2. The q is 1, t1 is minus 3, t2 is t2 is 4. So this gives the value of t as a minus of 7. Okay, and this completes the third step of this algorithm. Then again you do the shifting. So your new value of a is 8, the new value of b is 4, the new value of s1 is minus 1, the new value of s2 is 2, the new value of t1 is 4, the new value of t2 is minus of 7. Okay, and for the value of a and b as 8 and 4, we can write as 8 is 2 times of 4 plus of 0. So the quotient is 2 here and the remainder is 0 here. So the value of q is 2. The value of r is going to be equal to 0. And for the value of q equal to 2 and s1 equal to minus 1 and s2 equal to 2, you can obtain the value of s based on that formula. So s is going to be equal to s1 minus q times of s2. s1 is minus 1, and that will gives the value of s equal to minus of 5. And the value of t can be obtained based on the formula of t1 minus q times of t2, where t1 is 4, t2 is minus 7, and q is going to be equal to 2. This gives the value of t as 18. Okay, so this completes the fourth step of this extended Euclidean algorithm. And then you do the one more shifting. So if you do the shifting, that a will become equal to 4, b will become equal to 0, s1 will be 2, s2 will be minus of 5, t1 will be minus 7, and t2 will be equal to 18. And then you will see that once the value of a is 4 and b is 0, then you cannot apply your division rule, because you cannot divide 4 by 0. So once one of the integer becomes equal to 0, at least b becomes equal to 0, you stop there. And then this non-zero integer, that's basically the GCD of your problem. So the GCD of 72 and 20 here is going to be equal to 4. Okay. If you take the value of s1 and if you take the value of t1, that's the value of your coefficient. S is going to be equal to 2, and the value of t is going to be equal to minus 7 here. Okay, so you have represented GCD of 72, 20, which is basically equal to 4, in terms of 2 times of 72 and plus minus 7 times of 20. Okay, so the coefficient value of s and t are 2 and minus 7 here. So in this example, we have seen how to apply the extended Euclidean algorithm and perform both the steps of computing the GCD and computing those coefficients s and t together, and represent all the steps of your extended Euclidean algorithm nicely in the form of a table, which is a clean way to represent your extended Euclidean algorithm steps. So I personally recommend to use this table approach to apply your extended Euclidean algorithm, where you can compute the GCD as well as those coefficients altogether. The last thing which we're going to study today is your arithmetic modulo m. So let z of m represent your set of non-negative integers which has the value less than m. So z of m contain all those integers starting from 0 and all the way up to m minus 1. Now if we are interested in doing some kind of a algebra and algebraic operation there, such that if we add 2 elements from this set and if you multiply 2 elements from this set, then the resultant element also belongs to the same set. Okay, so you can perform this arithmetic modulo m operations there. So the first operation is your addition operation. So the addition modulo m, which you write as a, and then plus, and then you put the sub m of b. So you read it as a arithmetic modulo mb is going to be equal to, you do the usual addition of a plus b and mod of m. Okay. And similarly, you can define the multiplication modulo m, where a multiplication modulo m with b is going to be equal to the usual multiplication of a and b and then mod of m. Okay. So take one example. If you have a 7 addition modulo 11 with 9 is going to be equal to, based on your definition, is 7 plus 9, which is the usual addition, which is 16, and mod of 11. And 16 mod of 11 is going to be equal to 5, because 16 can be written as 1 times of 11 plus of 5. So 5 is the remainder here. So the value of 16 mod 11 is equal to 5. Okay. Similarly, you can solve the problem with respect to the multiplication modulo. So 7 multiplication modulo 11 with 9 is going to be equal to, based on the definition, is going to be 7 times 9, which is the usual multiplication mod of 11. So it's going to be 7 times 9 is 63 mod 11, and 63 mod 11 you can represent as 63 is going to be equal to 5 times of 11 plus of 8. So the remainder here is going to be 8. So the value of 63 mod 11 is going to be equal to 8. So there are various properties which this arithmetic modulo m will hold. So the first is your closure property. So according to the closure property, if a and b are the element from your Z of m set, then if you apply your addition modulo m and multiplication modulo m operation between those two elements, so the resultant element a addition modulo m with b and a multiplication modulo m with b, they are also going to belongs to the same set. So that means you have the closeness property. The second is your commutative property, which is similar to your usual arithmetic operation. So a addition modulo m with b is going to be equal to b addition modulo m with a, and a multiplication modulo m with b is going to be the same as b multiplication modulo m with a. You also have the associative property here, so with respect to the addition and with respect to the multiplication. So a addition modulo m with b and then addition modulo m with c is going to be equal to a addition modulo m with b addition modulo m with c. And similarly, a multiplication modulo m with b and multiply with the multiplication modulo m with c is going to be equal to a multiplication modulo m multiply with b multiplication modulo m with c. You also have a concept of identity element. So with respect to your addition, you have a for an element a, addition modulo m with 0 is going to remain the element a itself. And with respect to your multiplication modulo m, if you take an element a and do the multiplication modulo m with 1, is going to remain the same element a. Okay, so you have the additive identity here, with 0 is the additive identity for an element a and 1 is the multiplicative identity with respect to the element a. You also have the concept of additive inverse. So the additive inverse of 0 is 0, because 0 addition modulo m with 0 is going to be equal to 0, and the additive inverse of any other element a is going to be equal to m minus a, because a addition modulo m with m minus a is going to be equal to 0. So for example, if we do a usual addition, so 2 plus minus of 2 is going to be equal to 0. So with your usual addition, minus of 2 is the additive inverse of 2, because if you add 2 and minus of 2 together is going to be equal to 0. In terms of your addition modulo, you are saying, while with respect to addition modulo m, you are saying, for example, of 2 addition modulo with 5, then you have to add 3 here such that that will become equal to 0. So 3 is going to be the additive inverse of 2. Okay, so 3 is the additive inverse of 2. Okay, and you also have the distributive property here. So you have the left distributive property and you have the right distributive property with respect to your addition modulo m and multiplication modulo m operations, which is similar to your classical arithmetic operations. Okay, so this arithmetic modulo m is an important operation. Say if let's suppose you want to do some application problem where you are interested in applying some set of operations of addition and multiplication in such a way that if you take two elements from this set and if you add them together and if you multiply them together, the resultant element still belongs to the same set, and then you have this concept of arithmetic modulo m. Okay, so this was just a brief introduction of your arithmetic modulo m, and in our next class we're going to learn about the last topic of this course, which is about the integer representations. So thank you.